Good afternoon, everyone. Good afternoon. I welcome you all again to the NEET Elite. Hope all of you are doing great, having the good time. People, if I'm audible and visible to everyone, just hit the chat box with the thumbs up fast. Just hit the chat box with the thumbs up fast if I'm audible and visible to everyone. Good afternoon, everyone. Good afternoon. Welcome you all again to the next session of the States of Matter on NEET Elite. Wonderful, guys, wonderful. How are you all doing? Tell me in the chat box fast. Thank you, Jayant. Thank you, Jayanti. Thank you. Organic chemistry bhi hogi. We'll do the organic chemistry as well. You just wait. We have just started. It's just been a week. Just give me some time. I'll finish everything of yours. Just wait. Wonderful, guys. Great. Yes, I'm done with my lunch. What about you guys? Are you done with your lunch? Okay, good afternoon, everyone. Good afternoon. Walaikum salam. Okay, so people, as you all must be familiar with the fact, today we are going to talk about one of the most important topics from the chapter States of Matter, right? And what is the name of the topic? We are going to talk about the compressibility factor versus the pressure curve, and at the same time, we are going to talk about the van der Waals gas equation, right? And before starting today's session, as you all must be knowing, we are supposed to introduce ourselves, and as you all must be knowing now, my name is Wassim Sir and I am your chemistry master teacher over here, right? Great, guys, great. So before starting, as you all must be knowing, we are supposed to like, share and subscribe so that everyone gets benefited from this channel, guys. So let me know if you did it. Let me know if you did it in the chat box fast. Let me know if you shared it. Let me know if you shared it fast, guys. Let me see the josh of the session. Give me the thumbs up. Give me the thumbs up fast. Wonderful. Great. So people, before starting today's session, let me again brief you about the Vedantu Pro subscription, Vedantu NEET Pro subscription, what this Pro subscription is all about, and what all things you are going to get if you are going to get this Pro subscription, right? What all things you are going to get in this Pro subscription. Let me tell you first, okay? People, if you are getting this Pro subscription, then apart from your live online teaching on YouTube, what all things you are getting apart from the YouTube sessions, you are getting the 5,000 plus hours of live online teaching with us, okay? The regular tests and assignments will be given to you, okay, which contains more than 10,000 questions, right? And you'll get to know the continuous review of your areas of improvement, right? And people, over here in this Pro subscription, we have got 20 plus teachers with 5+ years of experience who will be helping you out in your NEET preparation if you are going to get this Pro subscription. And what is the best part in Pro subscription, guys? If you are getting it, you are definitely going to get the personal attention of the teachers, right? You can talk to your teachers live during the session, okay? You are definitely going to get the personal attention from all the teachers from physics, chemistry or biology, right? Okay, and you have got complete liberty. Either you want to learn in English or Hindi, the choice is all yours, okay? You have to select it, and we are going to cover everything including the micro courses and the crash courses in this Pro subscription, right? Nitesh, this is not the first lecture, bro. This is not the first lecture. This is, I guess, the 7th or 8th lecture of this chapter. Okay, now let me talk about the Pro subscription for the people who are going to appear in NEET 2021. People, if you guys are getting this, what we have come up with, these 3 monthly plans, and over here you can see the 20% discount is on every plan. 1 month plan after discount is going to be just for 6K, okay, and similarly 3-month plan is going to be for 16.8K, and the 6-month plan is going to be for 31.2K with the 20% off, right? Very nice it is, and reasonable price, I would say. Yeah. Okay, talking about for the people who are going to appear in the NEET examination in 2022, we have again come up with the different plans for you guys as well, and you can see over here again we have got 20% off, right? So 1 month plan after 20% discount is just going to be for 4K. Similarly, 3-month plan is just going to be for 10.8 and so on. This is for the people who are going to appear in NEET 2022, right? talking about the droppers, right? As I always say, today's droppers are tomorrow's toppers, right? For the NEET droppers, guys, again we have come up with some plans, with some beautiful plans. You can see 1 month plan after the 20% discount, you are going to get it for 7.2k, and similarly 3 month plan you can take for 20.4, 6 month plan after discount you are going to get for 40.8 for the people who are going to, for the droppers, right? In general, I'm saying. Wonderful, guys. And the point is how to avail this discount. What you are going to do is, there's a link in the description box, guys. Just click on the link and use this coupon code WSPRO, and you are going to get 20% discount if you are using this coupon code in any sort of subscription, whichever you want to like, right? Okay. So people, are you damn excited for the today's session? If you are damn excited for the today's session, give me the thumbs up again. Let me see the josh of today's session. Give me the thumbs up. Fast. I'm looking at your chats. Give me the thumbs up fast. Wonderful. Great. I want a lot of thumbs ups, guys. Yeah? Great. Well, guys, you can ask me doubts anywhere on Telegram, Instagram, wherever you find me. Just ask the doubts, whatever doubts you feel like asking, okay? Got it? So let's move on to today's topic, in which we are going to talk about the variation of compressibility factor with the pressure, okay? What happens to the compressibility factor Z on changing the pressure, right? Okay, so let's move on and let's talk about this topic a bit in detail. Let's see what happens to the compressibility factor on changing the pressure of the gas, okay? People, before coming into this topic, okay, before starting this topic, let me tell you a few basic and important things which you must know before starting the session, okay? Those important and basic things I'm writing over here for you. For example, see, let's say I have got two gas molecules over here. Let's say these are two gas molecules over here. And let's assume the gas molecules right now are at infinite distance apart. Okay, remember, guys, the force of attraction between the molecules is inversely proportional to distance. If distance between the molecules is more, that means force of attraction between them is less. If distance between the molecules is less, that means force of attraction between them is more. Over here, right now, the molecules are at infinite distance apart. If the molecules will be at infinite distance apart, the force of attraction between them will be equal to 0, right? When the gas molecules are at infinite distance apart, the force of attraction between them is going to be 0, number 1, okay? Now, people, if I'll bring these molecules closer, after bringing these molecules closer, can I say distance between the molecules is decreasing? And if the distance between the molecules is decreasing, what is happening to the force of attraction? Force of attraction is increasing. So if I'll bring these molecules closer, distance between them is decreasing, force of attraction is increasing, right? For example, I'm giving you one scenario when the molecules will be over here, when these molecules would have come across over here, right? And this is the scenario when the molecules are at maximum closest distance. This is the scenario when the molecules are at maximum closest distance, right? And when the molecules will be at maximum closest distance, force of attraction between them is going to be maximum at that time. Force of attraction between them is going to be maximum at that time. So initially, the molecules were at infinite distance apart, force of attraction between them was 0. Now the molecules are coming closer, force of attraction is increasing, and this is the scenario when the molecules are at maximum closest distance, right? And when the molecules are at maximum closest distance, force of attraction between them is going to be maximum, right? Number 1. Number 2, if I want these molecules to come little more closer, what is going to happen? Force of repulsion will start between the molecules, okay? After this point, if I want these molecules again to come a bit more closer, what is going to happen? Force of repulsion is going to start between these molecules. So people, can I generalize a statement? When the molecules were at longer distance, at the larger distance distances. Can I say at that time force of attraction was there between the molecules? And when the molecules are very, very close, if I want these molecules to come a little more close, what will happen? Force of repulsion will start between them. Okay, so can I generalize a simple statement? The attractive forces are long range forces. The attractive forces are long range forces, and repulsive forces are short range forces. Repulsive forces are short range forces. Just hit the chat box with the thumbs up if you got this concept. Just hit the chat box with the thumbs up, guys, if you got this concept. Tell me fast, tell me fast. Wonderful, wonderful, guys. Great, great, great. So remember, attractive forces are long range forces, and repulsive forces between the molecules is going to be short range forces, right? Yes, yes, yes. Yes, we are going to solve problems also. Yes, yes, yes. Definitely, yeah. Okay, let me move on, guys. Let me move on. I'm sure this concept is clear to you. Let me move on to one more important thing over here. And what is that? Have a look. What is that? Have a look. Guys, if you remember, in the last session, we talked about the compressibility factor, Z, compressibility factor Z, and Z was equal to observed volume divided by ideal volume. What do we mean by this? Just have a look. Let's say I have got a container over here. Let's say I have got a container over here. Let's say I've got two containers, okay? I've got two containers over here. And in this container, I'm keeping 1 mole of ideal gas, for example. I'm keeping 1 mole of ideal gas. And in this container, I'm keeping 1 mole of unknown gas. 1 mole of unknown gas. I have no idea whether the gas inside the container is real or ideal. Now people, if both the gases are kept at same pressure and temperature, we know 1 mole of ideal gas at fixed temperature, or let me say the gases right now are at STP. Both the gases right now are at STP, right? Both the gases I'm keeping at STP. And we already know 1 mole of ideal gas at STP, it occupies the volume of 22.4 liters, right? So volume of this ideal gas, which I'm representing by VI, is going to be 22.4 liters over here, correct? Let's say the volume occupied by this unknown gas is represented by V naught, and V naught I'm calling as the observed volume. V naught I'm calling as the observed volume. Correct? Now people, if the value of Z, if the value of compressibility factor for this unknown gas, if it comes to be equal to 1, what can we conclude from there? If the value of Z for this unknown gas is equal to 1, then I would say observed volume of this gas is going to be equal to the ideal volume. Can I say at that time the gas which I have kept inside this container, this gas is going to be ideal at that time? The gas is going to be the ideal. We know that, right? We have discussed the same thing in the last session, if you remember. Okay, now people, if the value of Z is not equal to 1, if the value of Z for this unknown gas, if it is not equal to 1, I would say volume of this unknown gas is not going to be equal to the volume of ideal gas, and I will be calling this unknown gas at that time as the real gas, right? I would be calling it as the real gas. Very, very simple. And in the last session, if you remember, there were two things in this Z is not equal to 1 category. The first one was if the value of Z is less than 1, and the second one was if the value of Z will be greater than 1. If the value of Z for this unknown gas is less than 1, first of all, the unknown gas is going to be real, and which forces are going to be dominating over here? Attractive forces are going to be dominating over here in this unknown gas, in this real gas right now, correct? Similarly, if the value of Z for the same unknown gas is coming out to be greater than 1, that means the gas inside this container is going to be real, and which forces are going to dominate in it? Repulsive forces are going to dominate in it. This is something which we have discussed in the last session, right? Now people, I have to tell you one important thing over here. And what is that important thing? Have a look. See guys, the value of Z, that is compressibility factor. Just give me a second. The value of Z, just a second guys. The value of Z over here for this unknown gas is equal to V naught divided by VI. Correct? This is the value of compressibility factor. Now people, see, understand one thing. For example, the value, if I'll decrease the value of Z, if I'll decrease the value of compressibility factor for this gas present in the container. If I'm decreasing the value of Z, decrease in the value of Z. What does that mean? If the value of Z is decreasing for the gas present in this container, can I say this numerator is decreasing basically? Numerator is decreasing. So V naught value is decreasing basically, then only this value of Z is decreasing. V naught value is decreasing. If the value of Z is decreasing, V naught value is decreasing. V naught is the volume of this gas right here. V naught is the volume of this gas right here. That means volume of this gas is decreasing. If the volume of this gas is decreasing, can I say molecules of this gas are coming closer? If the molecules of this gas are coming closer, can I say distance between them is decreasing? And if the distance between the molecules over here is decreasing, can I say force of attraction is increasing? Definitely force of attraction is increasing, right? Definitely force of attraction is increasing. So remember from now onwards, when for a real gas Z value decreases, what does that mean? That means force of attraction between the molecules is increasing. Correct? Decrease in the value of Z leads to increase in the force of attraction between the gas molecules. Very, very, very simple. Correct? Now people, if I'll increase the value of Z, if I'll increase the value of Z for this real gas which is inside the container, if I'll increase the value of Z, increase the value of Z, what does that mean? That means this numerator term is increasing, V naught is increasing, V naught is increasing. On increasing the value of Z for this gas in the container, what will happen? V naught value will increase. And what is this V naught? V naught is the volume of this real gas, correct? V naught value is increasing, volume of this gas is increasing. If the volume of this gas is increasing, can I say molecules are going far from each other? If the molecules are going far from each other, can I say distance between them is increasing? And if the distance is increasing, force of attraction is decreasing. Force of attraction is decreasing, right? So increase in the value of Z, increase in the value of Z leads to decrease in the force of attraction between the molecules. Increase in the value of Z leads to decrease in the force of attraction between the molecules. People, if this thing is clear to you, just hit the chat box with the thumbs up if both these statements are clear to you. Very, very simple. If for a gas inside this container, if for a real gas inside this container, Z value decreases, that means force of attraction between the molecules increase. Okay. Similarly, if the value of Z increases, that means force of attraction between the molecules decrease. Or I would say, if the force of attraction between the molecules is decreasing, I can say, in other words, force of repulsion will start to increase. If the value of Z increases, I would say force of repulsion between the molecules will start to increase. Correct? Very, very simple. Remember this. This is the most important point over here, right? Increase in the force of attraction more means decrease in the value of Z. Decrease in the force of attraction means increase in the value of Z. Correct? Force of attraction decreases, that means force of repulsion will start to increase. Correct? Now people have a look. Now people have a look. Now people have a look. Just give me a second. Just give me a second. Just give me a second. Now, this is the topic which we have to discuss in the today's session. Well, a lot of people are saying, sir, please increase the brightness of the board. I think brightness is perfect. People, should I increase the brightness of it? Then it might take some time. Tell me fast, tell me fast. Should I increase the brightness of it? I think it's perfect, right? Yeah, great, 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 great. You just increase the brightness of your screen, guys. That's one and the same thing. Okay. Have a look, guys, have a look. Now, what we are going to do is, this is something important. This is something important, okay? Understand it properly. Understand it properly. See, guys. What am I going to do over here? Again, I'm going to take the container. Again, I'm going to take the container in which I have got 1 mole of real gas. 1 mole of real gas now, okay? And in this container, I have got 1 mole of ideal gas. I have got 1 mole of ideal gas, okay? Volume of this real gas, which I call as observed volume, denoted by V naught. Volume of this ideal gas, which I'm denoting by Vi. And both the gases are kept at same pressure and temperature. Both the gases are kept at same pressure and temperature, right? Till now, what we got to know is, we got to know if the value of Z decreases, force of attraction between the real gas molecules increase. Force of attraction between the real gas molecules increase. And if the value of Z increases, if the value of Z for the gas increases, force of attraction between the real gas molecules that decreases, or I would say force of repulsion will start to increase. Okay, this is something which I told you right now. Okay, now people have a look. This is the curve which I'm plotting between Z compressibility factor versus pressure for a real gas at 0 degree centigrade, right? I'm keeping the temperature of the real gas fixed at 0 degree centigrade, correct? Now people have a look. This is the curve which is made at 0 degree centigrade. Now I'm drawing a line over here. Parallel to pressure axis. And let me tell you, this line represents Z is equal to 1. This line, its equation is Z is equal to 1. If the value of Z for this line is equal to 1, can I say this line represents the ideal gas? Definitely it's going to represent the ideal gas, correct? Very, very simple, because Z value is 1, right? Now people, the region above this line, that region is basically Z greater than 1 region, and the region below this line, that is going to be Z less than 1 region. And we know whenever for a gas Z value is less than 1, which forces are dominating? Attractive forces are dominating, right? Attractive forces are dominating, and in this region Z value is greater than 1, so I would say repulsive forces will be dominating, right? So region above this Z is equal to 1 denotes your repulsive forces are dominating, and region below this Z is equal to 1 says attractive forces are dominating in this region. Very, very simple. Now people see something important. See, this is the line for the ideal gas. Now real gas are not going to follow the same curve. Because for the real gas, Z value is not equal to 1. Z value is equal to 1 for the ideal gas. So what should be the curve for real gases? For most of the real gases, the curve looks like this. For most of the real gases, the curve looks like this. Or let me make it like this. Just give me a second. Let me make it like this. See, for most of the real gases, the curve looks like this. Okay, this is valid for real gas, and this straight line is valid for ideal gas. Now people, we have to conclude 5 important things over here. What is that? Have a look. Let's say I'm denoting this point by A. Let's say this is the point which I'm denoting by B. This is the point which I'm denoting by C, okay? And this is the point over here which I'm denoting by D. Understand properly. See, if I'll take this point over here, this point over here at the origin, can I say at the origin pressure is approaching towards 0? At the origin pressure is approaching towards 0, and I'm making this curve at constant temperature, and at constant temperature, if you remember, pressure and volume both are inversely proportional. Now people, this point, it denotes that the pressure of the real gas is 0, is approaching towards 0. If the pressure of real gas is approaching towards 0, can I say its volume will be approaching towards infinity? So at this point where the pressure approaches towards 0, volume of the real gas is approaching towards infinity. If volume of the real gas is approaching towards infinity, can I say molecules will be at infinite distance apart? And when the molecules of the real gas are at infinite distance apart, can I say there will be 0 force of attraction between them? And any gas in which the molecules will have 0 force of attraction between them, that gas is what we call as ideal gas. So can I say every real gas behaves like the ideal gas at very, very, very low pressures? That's why I started the curve of the real gas from this point, where the Z is equal to 1. Very, very simple, right? Why? Because at this point, pressure approaches towards 0, volume is approaching towards infinity, molecules will be at infinite distance apart. If the molecules of the real gas are at infinite distance apart, there is no force of attraction between them. If there is no force of attraction between them, then this real gas at very, very low pressure is going to behave like the ideal gas. That's why I started the curve of real gas from this point where Z is equal to 1. Correct? Very, very simple. Now people, understand one more thing. If I'll go along this axis, if I'll go in this direction, along positive x-axis, positive pressure axis, if I'm moving along this way, that means I'm increasing the pressure, I'm increasing the pressure of the real gas, If I'm increasing the pressure of the real gas, initially over here at this point, The molecules of the real gas were at infinite distance apart. There was no force of attraction. The real gas was behaving as the ideal gas. Now I'm increasing the pressure. On increasing the pressure, volume of the gas will decrease. If volume will decrease, can I say molecules will come closer? If molecules will come closer, can I say distance between them decreases? If distance between them decreases, can I say force of attraction between them increases? Force of attraction between them increases. On increasing the pressure, force of attraction between the real gas molecules, that is increasing. And if the force of attraction increases between the real gas molecules, what happens to the value of Z? Value of Z decreases. Value of Z decreases. Very, very simple. So guys, have a look. Or if I'm moving along this axis, this way, if I'm moving along this way, what is happening? Pressure of the real gas is increasing. Volume is decreasing. Molecules are coming closer. Force of attraction between them increases. Z value is decreasing. That's why this curve is coming down like this. Because Z value should decrease, because force of attraction is increasing, right? Z value is decreasing, Z value is decreasing, force of attraction is increasing, force of attraction is increasing. Can I say this is the minimum Z value for the gas? This is the minimum Z value for the gas, right? This is the minimum Z value for the gas. And when the Z value will be minimum, can I say at that time force of attraction between the molecules will be maximum? So at this point B, the force of attraction between the molecules is going to be maximum. It is going to be maximum. That means this B point denotes that the molecules are at maximum closest distance. Molecules are at maximum closest distance. Over here at this point, molecules were at infinite distance apart. They were at infinite distance apart. At this point, I would say the molecules are at maximum closest distance, where the force of attraction between the molecules is maximum, right? Now people, this point represents that the molecules are at maximum closest distance. If I'll increase the pressure little more after this, which forces will start? Which forces will start? I would say repulsive forces will start, right? Because this is the scenario when the molecules are at maximum closest distance, where the force of attraction between them is maximum. Now, if I increase the pressure a bit more, what will happen? Force of repulsion will increase. Force of repulsion will start to increase. And force of repulsion increases, that means Z value increases. That's why the curve is going up. The curve is going up, it means force of repulsion is increasing. On increasing the pressure from this point, on increasing the pressure after this point, the force of repulsion between the molecules is increasing. Force of repulsion between the molecules is increasing. And this at point C, force of attraction between the molecules is going to be equal to the force of repulsion. At this point C, the force of attraction between the molecules is going to be equal to the force of repulsion between them. If the force of attraction and the force of repulsion is going to be same, can I say the net force on the molecule is going to be 0? The net force on the molecule is going to be 0. And in which gas the net force on the molecule is 0? We call that gas as ideal gas. Can I say at this point again, the real gas is behaving as the ideal gas? At point C, the real gas is again behaving as the ideal gas. Correct? Very, very simple. At this point, the real gas again is behaving like the ideal gas. Now people have a look. If I'll increase the pressure little more, what will happen? I would say now repulsive forces are going to dominate. Because repulsive forces are short range forces. People, just hit the chat box with the thumbs up if you got this curve properly. Just hit the chat box with the thumbs up if you got this curve properly. Let me know fast. Let me know in the chat box if you got it. Tell me guys fast. Wonderful. Great. Wonderful, guys. Yes, Ma, I'll see your doubt. Okay, wonderful. Great, guys. Great. So should I move ahead? And talk about a few more important things? Yeah. I'm moving ahead and I'm going to talk about few more important things. I'm sure this compressibility factor versus pressure curve is clear to you. I'm sure you can easily say why the real gas follows this curve and why the ideal gas follows this straight line. Correct? You can easily tell it from now onwards. Right, guys? So what am I going to do is I'm going to erase everything and let me tell you few more important concepts over here. Understand properly, okay? Let's say this line represents Z is equal to one line. That means this line represents your ideal gas, right? Let's say I've got, okay, I'm drawing one line over here. Let's say this is the curve for a real gas A. Let's say this is the curve for a real gas B. Let's say this is the curve for a real gas C, right? Can you tell me among which real gas molecules the force of attraction is going to be more? Can you tell me force of attraction in which of the gas is going to be more? Can you tell me that? Can you tell me that fast? Can you tell me that fast? I'm looking at your chats only. Just tell me, guys. What do you think? What do you think? What do you think? Which gas molecules will experience maximum force of attraction? Very, very, very simple. Very, very, very simple. See, guys. See. Have a look. Have a look. This is the minimum value of Z. Just a second. This is the minimum value of Z for gas number A. This is the minimum value of Z for gas number A. This is the minimum value of Z for gas number B. This is the minimum value of Z for gas number C. Minimum the value of Z, lesser the value of Z, more the force of attraction. See, guys, among these Z values, can I say ZC is going to be less than that of ZB, is going to be less than that of ZA, right? Lesser the value of Z, more the force of attraction. So can I say C has got lesser value of Z over here, so C gas molecules will have more force of attraction. So I would say force of attraction in in C is going to be maximum, followed by B, followed by A. Or I can generalize a simple statement over here. Let me tell you, for gas number A, this distance is what we call as dip. This is what we call as dip for gas A. Similarly, this distance from this point till this point, it's called as dip for gas B. From here till here, it's called as dip for gas C. Can I say more the dip, more will be the force of attraction, right? More the dip of the curve, more will be the force of attraction between the gas molecules. So remember, from now onwards, I'm writing it over here. More the dip in the curve, more will be the force of attraction between the molecules. More will be the force of attraction between the gas molecules. Very, very simple. Between gas molecules, correct? Very simple. Now, people, one more thing. One more thing. If I'll ask you, which gas among the three can be compressed easily? Remember, that gas is going to get compressed easily in which force of attraction already exists. Now, people, see, gas number C, it has got more force of attraction between the molecules, so it is easy to compress gas C over here. So I can say gas C can be compressed easily, followed by gas B, followed by gas A. Okay. If I'll ask you, which gas can be easily liquefied over here? What do we mean by liquefaction of gas? That means we have to bring the gas molecules closer. I would say gas C is going to be liquefied easily. Why is that? Because strong force of attractions are there between the molecules. So we have to do less amount of work to compress it more, to liquefy it more, right? So I would say gas C is going to get liquefied easily, followed by B, followed by A, right? So people, from this curve, you can relate the force of attraction between the gases, you can relate their compressibilities, you can relate their ease of liquefaction as well. I'm sure this is clear to everyone, right? So if the concept is clear to everyone, just hit the chat box with the thumbs up, guys, fast. Just hit the chat box with the thumbs up fast, so that I get to know the concept is clear to everyone. Priya, tomorrow this chapter is going to get over. Tomorrow we'll finish off this chapter, and day after tomorrow we are going to start a new chapter. This is something which we have discussed. As the Z value decreases, attractive force increases. As the Z value increases, attractive forces decreases, or repulsive force increases, right? This is something which we already discussed. More the dip in the curve, more is the force of attraction between the molecules. More is the force of attraction, easily the gas can be liquefied. This is something which we have discussed till now, right? Wonderful, guys. Great. Now let's talk about the Van der Waals gas equation. I'm not going to derive this Van der Waals gas equation over here. I'm going to tell you those points which can come in your NEET examination from your Van der Waals gas equation. So let's talk about this Van der Waals gas equation over here. Just a second, sorry. See, guys. For example, I have got an ideal gas. Let's say I've got ideal gas, okay? Let's say inside this container, I have got n moles of ideal gas. If I have got n moles of ideal gas inside this container, can I say it should follow the ideal gas equation? PV is equal to nRT. I can say that, right? Where P is the pressure of ideal gas, V is the volume of ideal gas, N is the number of moles of ideal gas, and T is the temperature of ideal gas. This equation is followed by ideal gas. But people, if you remember, in the ideal gas, is there any force of attraction or repulsion? There is no force of attraction or repulsion between them, right? What about the size of ideal gas molecule? Size of ideal gas molecule is negligible. Now, can you tell me, will the real gases follow this equation? Real gases are not going to follow this one, correct? This PV is equal to nRT. Why is that? Why is that? We have to do some modifications in this equation. Why? Because in the real gas, there are force of attractions or repulsions, and we cannot neglect the actual size of the molecule, right? But this equation does not account the force of attraction between the molecules or the size of the molecules. So what I'll be doing is I'll be adding or subtracting few things over here so that the new equation which gets generated, that will be valid for the real gas. Now what I'm going to do is I'm going to write a new equation like this. Pressure of a real gas plus delta P multiplied by, instead of ideal volume, I'm writing volume of real gas minus delta V is equal to nRT, Now people, let me tell you first of all, this equation will be followed by the real gases. This equation is going to get followed by the real gases, okay? Let me tell you this delta P, guys, this is what we call as pressure correction factor. This is what we call as pressure correction factor, and delta V is what we call as volume correction factor. It's what we call as volume correction factor. Now people, in this equation, this delta P, it accounts in the force of attraction between the gas molecules, okay? This delta P gives us the idea about force of attraction between the gas molecules, and this delta V over here, this gives us the idea about the size of the molecules. It gives the idea about the size of the molecules. And let me tell you, this delta V over here, which is called as volume correction factor, or we call it as excluded volume. We call it as excluded volume. Now people, one more important thing. Let me tell you this delta P, which is what we call as pressure correction factor, delta P, it is equal to AN square divided by V square. Right? The value of delta P, if you guys remember, it's going to be equal to AN square divided by V square. Similarly, the value of delta V is going to be equal to N multiplied by B. This is the value of volume correction factor. This is the value of pressure correction factor, and pressure correction factor accounts the force of attraction, okay? It gives us the idea about force of attraction between the gas molecules, and this delta V, it gives us the idea about the size of the gas molecules, right? Now people, have a look. This A and B over here, these are called as van der Waals constants. A and B over here are called as the van der Waals constants, right? Now people, few things which you guys are supposed to remember. Just have a look. See, more the value of A, just a second, I'm going to give you the significance of these. van der Waals constants. Have a look. More the value of A means more is the force of attraction between the gas molecules, right? More the value of A means more is the force of attraction between the gas molecules. And similarly, less the value of A means less is the force of attraction between the real gas molecules, correct? Similarly, if I'll talk about B, other van der Waals constant, more the value of B tells me that more is the size of the gas molecule, more is the size of the real gas molecule, okay? This is something important which you guys are supposed to remember. More the value of A in the van der Waals equation means more is the force of attraction between the real gas molecules, okay? More the value of B means more is the size of the real gas molecules. Very, very simple. Now people see. I gave you the value of delta P and delta V over here. Can I complete this equation now? Can I complete this equation now? Can I write it like this? P plus, instead of delta P, I'm writing AN square divided by V square multiplied by V minus, instead of delta V, I'm writing NB is equal to nRT. Now this equation is what we call as Van der Waals gas equation, which is valid for n moles of real gas. This is valid for n moles of real gas. N moles of real gas, right? It's valid for n moles of real gas. Number one. Number two, this A, more the value of A means more the force of attraction between the gas molecules. More the value of B, what does that mean? That means more is the size of molecules. Now the point is, what are the units of A and B over here? What are the units of A and B over here? Okay. Now people, let's talk about the units of A and B over here. See, I'm going to remove this part and let's talk about the units of A and B and their significance over here again. See guys, we got to know delta P, which is pressure correction factor, that is equal to AN square divided by V square, correct? Can I eliminate A from here? Can I say A is going to be equal to delta P V square divided by N square, right? So what do you think should be the units of A? See guys, over here I've got the term delta P, which means pressure. Pressure units I'm taking in atmospheres, right? Over here this is volume. Volume ka units I'm taking in liter, and this will be liter square. And over here divided by N. N represents the moles, so it's going to be ATM liter square mole to the power -2. This is going to be the unit of Van der Waals constant A over here. Now talking about the unit of B. Have a look guys. We got to know delta V is equal to NB, and I can say B is going to be equal to delta V divided by N. If I talk about the unit of B, delta V, which is basically volume, its unit I'm taking in liter, so it's going to be liter mole inverse, right? This is the unit of B over here, okay? This is the value of B over here, right? Very, very simple. People, tell me, is the concept clear to you? Is the concept clear to you? Tell me, so that I can move ahead and talk about few more important things over here. Tell me fast, tell me fast. Tell me fast. No, if B increases, size of the gas molecule increases. Yes, Firuk, that's what I'm going to tell you now. All right, I'm moving ahead guys, and I'm talking about few more important things over here. See guys, have a look. Just a second. Okay, if I'm plotting once again the curve between pressure and volume for a real gas, the curve between compressibility factor Z and pressure for a real gas at 0 degrees centigrade, okay? Now people understand. This line represents Z is equal to one line. That means this line is valid for the ideal gas. Okay. Now, for example, I have got three gases like this. This is gas number A. This is gas B. And this is gas C. Can you tell me which gas will have maximum force? Which gas will have maximum value of A? Which gas will have maximum value of A? Can you tell me that? Which gas will have maximum value of A? Which gas will have maximum value of A? Kishore, for hydrogen and helium, the curve will be like this, which we'll be talking in the next session, not here. Okay? I'm talking about the majority of the real gases. Leave hydrogen and helium aside. Okay, very, very simple, guys. See, we got to know more the dip in the curve means more the force of attraction, right? And more the force of attraction means more the value of A. So, A value for gas C is going to be more than that of A value of gas B is going to be more than that of A value for gas A. I'm sure this is clear to everyone. Okay, I'm sure this is clear to everyone. Now let's use all these concepts in some basic questions so that you get to know few important things. Okay, I have got a question over here. Very, very simple question. See guys, I have got two gases, gas A and gas B. Gas A is present in this container, gas B is present in this container, and I'm taking equimolar gases. Let's say I've got 1 mole of gas A over here and I've got 1 mole of gas B over here. Okay, 1 mole of gas B. Now people, for both the gases, the value of B is same. For both the gases, the value of B is same. But for gas number A value is more. For gas B, A value is less. Can you tell me which one of the following real gases has occupied more volume? What do you think? More volume. See guys, both the gases have got same value of B. If they have got same value of B, can I say size of both A and B molecules are going to be same? Size of both A and B molecules are going to be same, number one. Number two, value of A for this gas is more. That means more will be the forces of attractions over here in this gas, and less are going to be the forces of attractions in this gas. Correct? More force of attraction means that means gas molecules have come closer. If gas molecules have come closer, that means volume of this gas is going to be less. So I would say volume of gas A is going to be less than that of gas B. Why? Because in the gas A, force of attraction is more. Why? Because A value is more. Right? Very simple. Very simple. Can you tell me, among the same two gases, which gas can be easily liquefied? Can you tell me that? Can you tell me which gas can be easily liquefied? Size of both the molecules are going to be same. Now A has got more force of attraction, so I would say A can be liquefied easily. So ease of liquefaction, if I talk about both the gases, if I talk about the ease of liquefaction, I would say gas A is going to get liquefied easily than that of gas B. Right? Very simple. Very simple. Right? Wonderful, guys. I'm seeing a lot of options coming up. Wonderful. Great guys. Okay. So this was about the volume. This is about ease of liquefaction, right? Okay. We have got one more question over here. Can you tell me answer of this one? Which one of these real gases is more compressible? Which one can be compressed more? See, I have got 1 mole of gas A over here. 1 mole of real gas A. I have got 1 mole of real gas B. 1 mole of real gas B. A value for both the gases is same. Force of attraction in both the gases is same. But over here, B value is more for this gas and B value is less for this gas. Can you tell me which gas can be compressed more? What do you think? Which gas can be compressed more? Very simple, guys. See how I'll do it. See, first of all, the value of A for both the gases is going to be same. That means the force of attraction in both the gas molecules are going to be same. Okay, but the size is going to be different because B accounts for the size. B value for gas A is more. That means the size of gas A molecules are going to be more. What about the size of gas B? Size of gas B molecule is going to be less. When I'll start to compress it, can I say this is the electron cloud? This is the electron cloud of this molecule. This is the electron cloud of this molecule. This is the electron cloud of this molecule. When I try to compress it, can I say there would be repulsions between these electron clouds? Can I say there would be more repulsions between these electron clouds compared to these, right? Very simple. If more are the repulsions in this gas, I would say this gas cannot get compressed easily, or I would say this gas A is going to be less compressible than that of gas B, right? So gas B is more compressible over here. I'll write gas B is more compressible. It is more compressible than that of gas A. It is more compressible than that of gas A. Correct? Very simple question it was, and the conceptual one. Right? Shaik is asking what is electron cloud? That's something which we discuss in the atomic structure. I'm sure you would have discussed the quantum mechanical model in which you have got the shapes of orbitals, in which you got the concept of the electron cloud, orbital, everything. Okay? If you do not know, just remember every molecule has got the electron cloud around it. Okay? Every molecule has got the electron cloud around it. Electron cloud is a kind of negative charge. So there is going to be more repulsions because the size of electron cloud is more, repulsions are going to be more. If repulsions between the molecules are going to be more, it cannot be compressed easily. So it is less compressible than that of B. Okay? Very simple. Okay, let's talk about one more and the last one. With that, we'll end today's discussion, and let me tell you, tomorrow we are going to have the last session for the states of matter. Okay? I'm sure you would have enjoyed the session. I'm sure you would have enjoyed the chapter as well. Okay, guys. Okay, let's move on. See, what do you think? Which gas will liquefy easily? What do you think? For a gas to get liquefied easily, what all conditions a gas must satisfy? See, first of all, that gas can get easily liquefied which will have more force of attraction between them, right? More force of attraction means more value of A. So that gas can be easily liquefied, which will have more value of A. And that gas can be easily liquefied whose size is going to be less, so that we can compress that easily, right? Size is going to be less, that means B value must be less, right? So these are the two conditions which a gas must satisfy, then only it can get liquefied easily. So A value should be more, so that there is more force of attraction between the molecules, so that the gas can get easily liquefied, okay? Second, the size of molecules should be less, so that there won't be repulsions between the electron clouds at all. So which option suits it? Option number D. People, just hit the chat box if you got the concepts in the today's session. Just hit the chat box fast. Just hit the chat box fast. Let me see if you got the concepts of the today's session. Wonderful, wonderful, guys. Great. Deepak, tomorrow we have one more session left for this chapter. Tomorrow I'm going to tell you more important things, okay? And tomorrow we'll finish this chapter off. And the next chapter I'll start with base mole concept. Mole concept and equivalent concept will be the next chapter. Wonderful, great. Great, guys. Okay, so with this, let me take a leave. But before taking a leave, for the people who joined late, let me make you understand the Vedantu NEET Pro subscription, okay? People, if you guys do not know about the Vedantu NEET Pro subscription, this is something really interesting. By getting this Pro subscription, you actually get to know the Vedantu platform, in which we take the actual classes apart from YouTube sessions, okay? The Vedantu platform, where there are a lot of extra things apart from this YouTube teachings and all. What all things you are going to get if you are getting this Pro subscription? You are getting the 5,000 plus hours of live online teaching. Number two, we are going to conduct the tests and the assignments with 10,000 plus questions will be given to you. And good questions, good quality questions. At the same time, you are going to get to know about the review of the areas of your improvement. Okay, 20 plus teachers we have here with 5 plus years of experience who will be taking classes for you all, and it's completely your wish to choose the teacher. Okay. All right, and people, you have got the complete option to learn in English or Hindi, and at the end, let me tell you, we are going to cover everything which includes your crash course as well as micro course. Okay. Fida, I cannot show you the weekly schedule right now. Okay, but then I can tell you in the tomorrow session we are going to relate the van der Waals equation with the compressibility factor, which is again one of the most important topics from this chapter. Okay, and day after tomorrow we are going to start the mole concept, the epic mole concept. Okay, and in order to avail the discount for the Pro subscription, guys, if you are getting it, you are supposed to use this coupon code WSPRO. Link is in the description box. Just click on the link. You are going to use this coupon code. By using this coupon code, you are going to get 20% off, right? Shakir, I have no idea about that. Oh, molecular speed lecture isn't available. It's available. You just go to the V Enthuse channel, click on the videos. Don't go to the playlist. In the playlist, you can, it might be missed there. Just go to the videos. Just find the lecture number 7, I guess. Lecture number 7 was, I guess, the kinetic theory of gases, in which I would discuss the molecular speeds, right? Okay. Okay, and at the end, talking about the Telegram group. Okay, this is our Telegram group. The link is in the description box. Just click on the link. You'll get added to the Telegram group wherein you'll be getting to know about a lot of things. You'll be getting the notes in the form of PDF through the Telegram group. Okay, and at the end, please do like, share and subscribe the channel so that everyone gets benefited out of this channel. Please do that. Please share with your friends. I want this family to grow even bigger. Okay, now we have grown this family to 13K subscribers almost, right? I want this family to grow even bigger, guys. Okay, so please share, subscribe and like the channel so that everyone gets benefited out of it. All right, it was really nice meeting you today. I'm sure you have got the concepts of, whatever concepts we have discussed, I'm sure you would have got everything. So please go through the session again, and wherever you see any sort of difficulty, any sort of problem, do let me know personally on my Telegram or on my Instagram. You can text me on Instagram itself if you have any sort of doubt related to the session. Okay, any sort of question, any sort of problems, any sort of doubts, you can ask me either on Telegram or the Instagram. Okay, all right, guys, till then, see you guys tomorrow. Till then, take care. Bye bye. God bless you all and love you all at the same time. Bye.